Good evening, everyone in India, and afternoon or morning, wherever you are over the world. So I'm Preetha. I am currently pursuing a PhD at University of Illinois. Um, I guess the title of the talk, which generated some curiosity amongst the people I know, isn't actually that original. In fact, everything which is written within codes is what Oritra Ghosh, whom all of you know, tells me quite often every time I discuss my research. I think the more, okay, sorry, I'm just trying to, yeah. I think the more appropriate technical title of my talk should be Electronic Transport in Strain Superlattices of Graphene. I work with Professor Nadia Mason here in the Department of Physics. And the research I do is also part of the NSF-founded Illinois Materials Research Science and Engineering Center. So right now, I think the title of my talk might seem like just a garbled mixture of words, but I hope that by the end of this talk, some or hopefully most of those words would be understandable to you. So we'll first start with discussing what are superlattices in general. Then we'll have a brief discussion on some of the superlattices which have been experimentally realized in two-dimensional materials like graphene. Then we'll talk at depth on strain superlattices of graphene and the sort of devices our group studies in strain superlattices. And we'll discuss the transport characteristics of these devices and what it can tell us about the underlying electronic properties of the system. Finally, we'll talk about what are the things we are currently looking into such systems, what are the phenomena we hope to observe in future. And I know it sounds weird to put present after the future, but at the end of this talk, I'll talk about my present uh, and my a little bit about the fabrication issues I keep on having, and probably that will give you an idea into the life of an experimentalist or as an experimentalist who do the type of stuff we do. So to start off, you can think of superlattice as a periodic structure in which there has been an engineered periodic potential generated, which controls the behavior of the charge carriers. And the superlattice is expected to have functional properties which are different from the constituent materials of the superlattice. It was first proposed for semiconductors in 1970 by Esaki and Su, and since then semiconductor superlattices have been studied quite widely. And the idea was to generate new semiconducting materials with different band structures which can be custom built. So one of the first semiconductor superlattices to be developed in the lab was this gallium arsenide aluminum arsenide superlattice. You have alternating layers of these two semiconductors. These black regions correspond to can you see my cursor?
Yes.
Okay.
Yeah.
Okay, that makes things easier. So these black layers over here correspond to 6 atomic layers of gallium arsenide, and the white ones correspond to 4 atomic layers of aluminum arsenide. So while trying to understand the workings of a superlattice, in a very hand-wavy argument, you can think of a single layer of the semiconducting material as a single quantum well. So this whole thing in the left, which has a conduction band and a valence band and the energy levels corresponding to a single layer of semiconductor. And then you're repeating that layer multiple times, and the properties of the eschewing multi-quantum well structure will depend on the thickness of those layers, which govern the interaction between the layers. So the hope is, because of this interaction, there will be new bands generated, there will be different functional properties of the system, And the main idea was to have novel nanomaterials of any sort. So two-dimensional materials, as many of you might have heard of them, they're quite in right now, have functional properties which are quite different from the bulk material. And using two-dimensional materials as the building blocks, it is possible to develop new superlattices which will have the properties custom made according to your needs. So some of the techniques which are used for generating such superlattices, one of them is vertical stacking. For example, you can have single layers of molybdenum disulfide and tungsten disulfide. Both of them are semiconductors piled up on each other. And there's a superlattice which has been seen to have optoelectronic properties quite different from the uh, either of those two either of those two 2D materials. Unmesh spoke at length about this system, twisted bilayer graphene, and it has generated a lot of interest currently, especially because of these moire patterns which are generated all over the system, and that comprises of a superlattice structure. Then you can have strain generated in any of those systems because of lattice mismatch or because of some sort of topography below it. And that is another method of forming superlattices by stacking a 2D material on top of a patterned substrate. We will talk about this third method in detail in this talk. But so these superlattices can have different chemical properties. For example, in the structure which you saw right now, graphene was transferred onto a closed packed structure of silicon dioxide nanospheres. And what happened as a result is that the graphene, which is in touch with the top of each of the nanospheres, have greater strain, and the strained graphene, it was observed, have greater reactivity to diazonium salts. So when diazonium molecules react with graphene, these nitrobenzene groups are expected to adhere to the surface of graphene. And what was observed was if you have graphene which is on top of such nanospheres, then the nitrobenzene groups preferentially adhere to those regions which were on top of the nanospheres. And they also did electrostatic force microscopy, which shows that those regions which are in top of each of the nanospheres have a very different work function compared to the surrounding material. And hence, the idea is that because of this strain superlattice which is generated in the system, there are chemical properties which are slightly modified. We in this talk will discuss more about the electronic properties of graphene superlattices. So I think we can have a small recap of the electronic properties of graphene in general. Unmesh made my job a lot more easier by talking about this earlier, but just to recap, graphene consists of carbon atoms in a 2D layer of honeycomb lattice, which is not a Bravais lattice. However, if you consider these dissimilar points A and B as a single unit, then this unit cell is repeated throughout your system in a triangular lattice. So when you take the honeycomb lattice from the real space to the reciprocal lattice space, the Wigner-Zeit cell or the first Brillouin zone is also hexagonal in shape. And the most important points to note here is the gamma point, which is the center of the Brillouin zone. And these K points, K and K prime are two dissimilar points. However, there are three K points in the system which are similar to each other because of symmetry, and three K prime points which are similar. When you do use the tight binding Hamiltonian for just considering nearest neighbor interactions and solve it, you'll find that the energy of the system varies linearly with the momentum. And this linear dispersion relation is quite famous for graphene. Because what happens is, so you have the valence band and the conduction band, and they meet at the 6 points, the 6 K points on the Brillouin zone. Near those K points, you'll find that because of the linear dispersion, the bands look like cones, and they meet at this Dirac point, and they are called Dirac cones because near the Dirac point, the behavior of the charge carriers is similar to those of Dirac massless particles, and they obey the Dirac equation. So how does the transport characteristics, which essentially refers to the conductivity or the resistivity of the system, varies near this Dirac point? So when you're looking close to the Dirac point, you're essentially considering the low energy carrier states, and which means that you need to consider low temperature electron transport. Most of these measurements are done at a few kelvins, millikelvins, so on. So what happens is, in this graph on the right, you can see the resistance of the system plotted against the gate voltage applied to graphene. You can think of gate voltage as an estimate for the number of carriers which has been generated in the system. So as you increase the gate voltage, the Fermi energy level lies below the Dirac point initially to start with. The electrons are slowly filling up the valence band. In this region, the current is being conducted by the holes. And as you can see, as more and more electrons fill up the band, the number of available holes for charge transport decreases. And so the resistance of the system shoots up. Once you reach the Dirac point, theoretically, there is no state available for the charge carriers, for the electrons, because of which there are no charge carriers which can occupy this state. And so theoretically, the resistance of the system should shoot up to infinity. But what happens in reality is that the Dirac point is never reached precisely. There are always charge impurities, mechanical deformations, etc. in graphene. So it, in general, in the lab, reaches a very high but finite resistance value. Beyond the Dirac point, again, as the Fermi level now lies, start filling up the conduction band, and there are more states readily available to the system. So the resistivity again goes down. So if you look at the resistance of graphene, even before considering superlattice effects, as a function of gate voltage, you'll see this sort of a peak, and the peak is at the Dirac point, and the conductance obviously is going to be the opposite of this, so it'll be like a V-shaped curve. We'll come back to this later in detail. So another superlattice which I wanted to discuss, this was done by Corey Dean's group, in case I have missed the reference here. So in this experiment, what they did was encapsulate a single layer of graphene in 2 layers of, so these are, I think, 5 atomic planes of hexagonal boron nitride. HBN is an insulator, and that is why it is very good for encapsulating graphene if we want really clean resistance results, because otherwise the charge carriers impurities from the substrate, the silicon dioxide silicon system, might interfere with the transport characteristics. So they had that encapsulated graphene system placed on top of this patterned silicon dioxide silicon chip, and on the silicon dioxide chip they had a triangular lattice which was created, and they used this silicon gate as a backgated device. So you can essentially apply an electrostatic potential in graphene, which will have this sort of a triangular lattice structure, and thus generate some superlattice effects. They also have a separate metal gate on top, which gives you an independent control over the number of carriers. And so the total carrier density is going to be a combination of both the top gate voltage and this backgate voltage, which we are calling the superlattice potential. So if you look at the resistance data of such a device, on the y-axis over here, you have the superlattice potential, which is the backgate voltage varying. And on the x-axis, you have the carrier density changing independently using the top gate potential. So for zero superlattice potential in the middle, you see that the resistance increases to a maximum as is expected for graphene and then decreases again. However, if you increase the superlattice potential, these additional features show up, extra peaks, and this is more evident if we take a cross section of this data. So what you'll find is that on this top left panel, this blue curve corresponds to zero superlattice potential. You have the normal resistance peak at Dirac point. But if you increase the superlattice potential, if you change it to plus or minus 50 volts, this additional peaks show up in the transport characteristics. They also did DFT calculations to look at how the band structure will look under these superlattices, so under these potentials. And for plus 50 volts, this is sort of what the band structure looks like. And they also find that for the density of states, as compared to zero superlattice voltage, which is this blue curve, the density of states for a plus 50 volts superlattice curve varies quite a lot. So another thing to note is that these colored regions correspond to the different bands filling up in the band structure. So for example, this blue region corresponds to this blue band over here filling up with electrons. So that was interesting, which was seen. Some effects of a superlattice, which was created using a patterned backgate. What our group has been trying to study for the past few years are strain superlattices using patterned substrate. So the idea is to spin coat a solution of nanoparticles. We use nanospheres initially, silicon dioxide nanospheres onto a silicon dioxide silicon chip. And it was found that these nanosphere form these hexagonal closed packed structure on their own. There are large areas, polycrystalline areas, and you can find very regular closed pack structures of these nanoparticles. And then graphene was wet transferred onto the system. So what happens is, as the graphene settles down on top of the nanoparticles, it stretches in those regions which are in contact with the top of the nanospheres. So these regions will have more tensile strain while it remains suspended in the middle region. And hence you have created a varying, a non-uniform strain superlattice in your graphene layer, which has a hexagonal closed packed structure. So this is an atomic force micrograph of one of my actual devices. I find it really pretty and I thought I'd include it. You can see each of those nanoparticles over here looks like sweets. And then you have the graphene layer in this bottom half of the image. You can see there's some random white stuff. I think they're probably just impurities present on surface of graphene. But this is just a monolayer of graphene on top of nanoparticles. So before going into detail about the strain superlattice effects on the electronic properties, it's important to understand how do we actually quantify the amount of strain which is generated in such systems. And the simple one-word answer to that is Raman spectroscopy. So just to recap, in Raman scattering, you have an incident wavelength of light coming into your sample, and on interaction with the sample molecules, the scattered light can have either the same energy or a different energy. If it has the same energy, then it's called Rayleigh scattering. If the energy changes, then it's Raman scattering. And it usually happens because of interaction between the oscillations of the incident light and the molecular vibrations of the sample. So usually in a Raman spectroscopic setup, you'll have laser of a certain wavelength. Usually we use 532 nanometers over here. That wavelength is focused, the light is focused onto your sample, then the collected light passes through a filter, and where you remove the original incident laser component, and you look at just the scattered light in a spectroscope in the detector. So what a typical Raman spectra looks like, you'll have a very sharp peak at 532 nanometers, which was the incident laser. This also has the Rayleigh scattering component. And then you'll see these other peaks, intensity peaks, show up elsewhere at different wavelengths. And Raman shift is calculated as the difference between the wave numbers of these peaks. So how much did what is the shift of these additional peaks which show up? And that is characteristic of the crystalline structure and the component of your system. So that gives you a lot of information about how your structure looks like, what are the elements in there, and so on. So for graphene specifically, you'll find that there are two most important peaks which show up. You have a G peak, which will be at 1580 centimeter inverse. And you'll find a 2D peak. If you're using a 532 nanometers laser, it will be at 2690 centimeter inverse. The 2D peak is actually a second order overtone of a D peak. The D peak is actually not seen in, it's supposed to be not seen in pristine graphene. In fact, the better the quality of your graphene, less the disorder, the D peak is going to be much lower. So you'll see that as compared to graphite, single layer graphene has a very sharp, very intense 2D peak. And so the intensity of the 2D peak, the ratio of the intensities of 2D peak to G peak gives you an estimate of how many layers of graphene there are in your system. So lesser the number of layers, higher will be this ratio. And the ratio of the D peak to the G peak gives you an idea of the disorder which is generated in the system. If you don't have much disorder, your D peak is expected to be lower. So with that in mind, let's look at how the Raman spectra varies with strain. So in these experiments, different flexible substrates were used for bending graphene. And what was found was that so in this graph, again, you have the intensity on the y-axis, the Raman shift on the x-axis. And what you'll find is as you increase the strain in the system, which correspond to these different curves in the upward direction, the G peaks slowly split into two peaks, G plus and G minus. And the 2D peak, although it doesn't split into peaks, have a shift happening. And if you plot this shift in the two G plus G minus peaks and the 2D peaks, what you'll find is that all of them follow a linear trend. So in the x-axis, which has somehow disappeared for this curve on the left, both of them are supposed to have the same axis. I'm sorry about that. But so the x-axis shows you the strain and the y-axis gives you the shift in the Raman peak. You'll see that all of them have a linear variation. And so if you can somehow estimate what the Raman shift is going to be for a certain known amount of strain, you can calibrate what the strain is going to be for different Raman shifts. In fact, there is something called Gruneisen parameters, which I won't speak about, which are sort of characteristic to your materials, which give you the slope of this curve. And you can also use those Gruneisen parameters for going from the Raman peak shift to the strain. Okay, so now we have some way of measuring strain in the system. This you need to keep in mind is the average strain over the system. So the local strain might be higher. What we are measuring is the average strain over a region of this graphene or nanospheres. And what was observed was that the average strain slowly decreases as the size of the nanospheres increase. And beyond 100 nanometers of diameter, there is hardly any significant strain left in your system. This is important. So in order to see effects of strain superlattices, for such a system, your size of the features need to be lesser than 100 nanometers or so. Okay, so let's now talk about the electronic transport in such a system. So this is a schematic of the device which was used for transport measurements, 2-point measurements. You have these gold leads deposited on either side. You pass a current through it, record the resistivity. All the measurement was done at 2 kelvins, and there is a gate voltage applied using this silicon electrode at the bottom, and that gives you control over the number of charge carriers in the system. So this is what the conductance curves look like. Let's look at this curve on the left first. So you have conductance or conductivity on your y-axis. The x-axis shows the number of charge carriers, and which again is tuned by the gate voltage. So this black curve corresponds to flat graphene, which is on a flat surface, no nanospheres present, hence not much of strain present. And that looks pretty similar to what you have for normal graphene, as we discussed earlier. But if you have nanospheres present, then there is some amount of strain generated in the system, and that corresponds to this differences. So if you plot the normalized conductivity for all the system, you see that apart from this dip at the Dirac point, which is expected, there are these additional kinks which show up in this regions I've marked with the red arrows. These kinks become more prominent as you increase the strain in the system. So this red and purple curve correspond to more strained graphene devices. And those kinks occur at a carrier density of 10 to the power 12 per square centimeter. And this was observed for all of those strains samples. So what is the origin of these kinks, which we call the secondary Dirac points? Because it seems like apart from the dip at just the Dirac point, there are these additional dips which are happening in the resistance, in the conductance. So we can theoretically calculate the carrier density, and turns out it matches the experimental results quite well. So if you consider a bird's eye view of the superlattice, the superlattice cell will, the strain superlattice will have a dimension of 21 nanometers approximately. And using that, you can estimate the area of this rhombus as a 4 into 10 to the power 12 centimeters square. And you need to include 4 electrons per supercell because there is a spin degeneracy of 2. And in graphene, since the K and the K prime points are not equivalent to each other, and there are 2 atoms present in your unit cell, you'll have an additional Valley degeneracy of 2 electrons. So total, there will be 4 electrons per supercell. And so you can estimate if you had 1 electron per supercell, your carrier density would be something. And then if you multiply that by 4, you get the desired superlattice carrier density, the carrier density per supercell. And the conductance dips happen when the supercell is completely filled up. So to explain it further, we assume what actually happens is that the strain leads to creation of certain gauge fields which can generate a pseudomagnetic field. Why is it called pseudomagnetic field? Because the effect of this field is very similar to what you would have if you have an external magnetic field. Because of this pseudomagnetic field, there are additional bands created near the Dirac point. So you can see that this curve over here, they meet fairly simply at the Dirac point. There will be more features which show up in this region, and that leads to the formation of the secondary Dirac points, which lead to those dips in conductance. And I thought I'd include expressions for the gauge fields and how they relate to the stress tensor elements. The beta is related with hopping between different lattice sites, and C and A are just constants related to the lattice parameters, and mu is a Lamech parameter. So we can, I think we have time for the magnetoresistance. So for magnetoresistance of flat graphene, which doesn't have any strain in it, shows something of this fan structure, which is called a Landau fan. And that happens because as the Landau levels, so again, on the y-axis, you have magnetic field. On the x-axis, you have carrier density. And what you'll see is that as you increase the magnetic field, there are more sub-levels, a different set of Landau levels which open up, which result in these features in the conductance data. But all of them come together and meet at the Dirac point. What you see is that if you apply the same idea to a system which has around 1% strain, then these additional messy stuff show up on the side. It doesn't make much sense right now, but it seems like beyond 4 Tesla, the effect of the strain is really not there, and the original fan diagram which you had is again regenerated. However, if you have a higher amount of strain in the system, then you see that these additional fans prop up along with the original fan in the middle, and those fans start from the secondary Dirac point. So this additional superlattice effects show up even in the magnetoresistance. We also collaborate with a group who do scanning tunneling measurements, and scanning tunneling measurements can give you local information of the band structure in any region of graphene. So I find this image to be really pretty. I think it's a Fourier transformed image, but you can actually see each of the graphene atoms over here, and that looks really cool. So by looking at the Landau levels and the energy where they occur, you can calculate the pseudomagnetic field which is generated in the system. And the preliminary measurements which we have done shows that a pseudomagnetic field as high as 55 Tesla can be generated, which is significant because if you know in the lab, we can generate maximum 7 or 8 Tesla magnetic fields. It's really impossible to go beyond that. So to be able to have such a high pseudo-magnetic field in the system opens up the opportunity for seeing a lot more of quantum phenomena. So what's next? What are we planning to see in these devices and future? What are we doing currently for this system? Something called zero magnetic field quantum Hall effect is expected for such strain superlattices. Because of the zero magnetic field, that might generate topological edge states, which might be detected on the non-local measurements of these devices. There are expected to be energy gaps opening up. If the system is under uniaxial strain, the electron transport is expected to be anisotropic. I'll explain this in a bit. And we also plan to move on to other 2D materials and seeing how the strain superlattices look for them. For example, for transition metal dichalcogenides, big name, but for essentially for materials like tungsten disulfide, tungsten diselenide, what happens under strain is that the band gap can be tuned, and also there are flat bands which are generated. These have a high density of states and have been seen to show quantum confinement. So I'll talk a bit now about the present and what I'm fabricating, how that is very interesting and sometimes very frustrating. So right now we're trying to study uniaxial strain effects on graphene. If you consider the previous diagram which we had of graphene on nanospheres, graphene was biaxially strained in these devices. If you want a 1D equivalent of such a system, you probably need to consider a set of parallel deformations. Let's call them parallel ridges because that's what they look like. So essentially a set of parallel lines on your substrate. This is not to scale, but what will happen is when you transfer graphene on top of this, the graphene will lie flat along the length of these rods, but in the transverse direction, it will experience periodic strain modulations. And so if we look at the resistance in the transverse direction and in the longitudinal direction, they're expected to be different from each other. And that's what we're trying to see. But the thing is, first we thought that, okay, let's use nanorods. They're the 1D equivalent of nanospheres. And we used nanorod solutions. However, as you can see from the scanning electron microscope images, the results aren't really good. Like in some cases, you'll have nanorods which are aligned parallel to each other. But for most of them, they just end up in this random orientations, and you really have no control over the alignment as such. So we thought we'd move on to electron beam lithography. If any of you have taken or plan to take the electronics optional paper, which I think is there in masters, you might learn a bit about lithography, but just to put it very briefly, um, in electron beam lithography, we usually coat the surface of our sample with some polymer, which is sensitive to electron beam. We use polymethyl methacrylate, PMMA in short. And then we focus the electron beam onto certain regions of this device which we want to expose. Then these electrons will react with the PMMA of those regions and will break some of the bonds. So when you do a process called developing, which is essentially dunking your sample into a certain solution, the PMMA from these regions will dissolve. And so you'll be left with a pattern which looks something like this. Then the next step is, for me, was depositing a metal. I used copper specifically as a mask. What is the mask will be clear to you in just a minute or so. So after that, we lift off the rest of the PMMA by using acetone. And so you're left with this copper features on top of your sample. Oops, sorry. And then we do something called reactive ion etching using carbon tetrafluoride gas, which will react with the particles of silicon dioxide and remove them. So all those regions which had copper on top will be masked and will remain. And once we have removed the copper using ammonium persulfate, we'll be left with whatever features we wanted on the silicon dioxide layer. So all we wanted was a set of ridges, right? It was a very simple procedure to think of in principle, but it's much more difficult in practice. So my pattern consisted of this set of parallel lines, and essentially the electron beam will expose over each of these lines. They were 10 microns, and we varied the width of these lines between 20 to 100 nanometers, because if you remember, if the features are wider than 100 nanometers, there isn't enough strain left in the system to see any effects. So these are details of the electron beam lithography process, but some of the things you can change is the voltage with which the electrons are accelerated onto the system, how the PMMA layer looks, the size of the electron beam, the current, the focusing, lots of parameters, and lots of things to mess up, as we did, or I did. So these are some of the very sad atomic force microscope images of what we ended up with. It wasn't really a set of parallel lines. You can have things bunching up, you can have things splitting. If you're very unlucky, your samples will look nothing like lines. Like this last image was really disappointing when I found out that's how my sample looks. The reason for that is you are really testing the limits of electron beam lithography over here, or at least the systems we have. The system we had a maximum accelerating voltage of 30 kilovolts. But in order to get really fine features, you need to have a very high accelerating voltage. Otherwise, it's impossible for those electrons to resolve the differences in the pattern. So after struggling with this over nearly a year, we realized that we needed to use some other system, and the one we were using was just not good enough. Luckily, we managed to get hold of another system which had 100 kilovolt accelerating voltage, and that worked so well. It was really nice to see. And we used this thing I can't pronounce, HSQ, as a resist. It's a negative resist, so I don't need to use the copper mask and everything. And so this is a scanning electron microscope image of my ridges. They are 60 nanometers wide, so we hope there will be enough strain in the system. And the spacing is 200 nanometers. So right now what I'm doing is transferring graphene onto the systems, making leads, and all of that, although the schematic and stuff look pretty simple, when it comes to actually fabricating them, there are lots of things which can go wrong. Graphene is quite delicate. So I hope to have a sample in for measuring later this month, hopefully next week. And that will be exciting because we can see whether there's any resistance and isotropy showing up in the data or not. So in summary, we discussed what a superlattice is. We looked at some ways of generating superlattices in two-dimensional materials. In particular, we looked at strain superlattices in graphene, which were fabricated using a specific technique of patterned substrates. The average strain can be measured using Raman spectroscopy. Then we studied the electron transport in the systems, and what was observed is that there are additional dips in conductance which show up, which are strain dependent. These conductance dips occur at secondary Dirac points, and we attribute this to the generation of a pseudomagnetic field, which creates superlattice mini bands. And some of the things we're looking into currently are possible quantum Hall effects at zero magnetic field, anisotropic transport, and similar effects in other two-dimensional materials. This is my research team. This is Nadia, my advisor. Ingje and Henry were both former members of the group who worked on this project. Ingje is now an assistant professor here at UFI. Henry, curiously, is a data scientist. These are our collaborators via the Illinois MERSEC, who do STM measurements, photocurrent measurements, etc. And these are my group members. I couldn't find an image of all of them together. These are the most recent images, but yes, with that, I'll open up the floor to questions. I hope you took something away from this talk, learned something new, and thanks for listening.
Thank you very much, Preetha. That was a wonderful talk. So now we shall be moving to questions. Okay, so I can see 3 raised hands. First, SC ma'am, then Ognihod, and then RC sir. So SC ma'am, please.
Navanita, can you go with the student questions first? I'll try to do later. Okay?
Okay, yeah. Okay, sure, ma'am. So Ognihoda first, and Shagnigda too.
Nice talk, Prithadi. I just want a quick question. Can you please go to the slide where you showed the Raman shift with the like the dependence of Raman shift on the strain?
Just a minute. I'll actually go there. Okay, give me a minute.
Yeah, just the graph. Yeah.
This one?
No, the next one, I guess, Raman shift versus the strain, the thing you said linear.
Oh, okay, I see this
Yeah.
one. Yeah.
So I just have like two small parts to the question here. So the first thing is, I can't, so can you explain me like physically, why exactly do we have the Raman shift decreasing with the strain? And why does it follow something linear instead of, let's say, quadratic or something like that?
So physically, the Raman shift is decreasing because essentially the Raman shift is is calculated as a shift in the peak positions, right? And that originate because the peaks originate themselves because of lattice vibrations. So if you have a certain amount of strain generated in the system, the molecule, the atoms are, the lattice is going to vibrate differently because of the strain. And so
Right.
the peak positions change because of that. And that is why there is a strain dependence of the Raman shift. Does that make sense for the first part?
Right. But, yeah, but what I want to ask is, why does it exactly decrease and follow a linear pattern? So that's what
Oh,
is.
I think this was something which was observed experimentally, and I don't know whether there's a theoretical explanation, or I'm not
Oh, okay.
aware of it at the moment.
So it may not
Like
be
this,
like very, okay. So it may not
yeah,
be very clear whether you have a microscopic theory of this or not.
I'm not sure of it. There might be,
Okay.
because there are certain uh, parameters called Grunizen parameters, which if you give me a moment, I can pull up. So this is the definition of Grunizen parameters. These are how they're defined. So like
Oh,
you have
okay.
the shear strain and the hydrostatic strain components, and you essentially estimate these parameters. For graphene, it is possible to estimate these parameters from a secular equation of the 2G energy mode. And usually like the experimental estimates give Grunizen parameters to be like 1.99, 0.99. So I'm not very sure about the details of
Okay.
the theory of this, but
Okay.
I'm sure there
Okay.
is one.
Okay. Thank you.
Okay, Shaknik, the next.
Hi Prithadi, thanks for the
Hi,
nice talk.
thank
So my
you.
question was about the Raman scattering measurements. So
Yes.
I was curious that you were using a 514 nanometer laser, that kind of wavelength. And
Yes.
so when you shine that kind of wavelength on your system,
Yes.
both the graphene layer as well as the nanospheres would also act like relevant scatterers, right?
Yes.
But how do you separate the scattering from the two?
So that is a good question, actually. The Well, I guess that means I sort of know the answer. But so the peaks which show up in a Raman spectra are characteristic of the material, right? So usually the graphene, for graphene, you know that the peaks are expected to show up in this region. So the Raman spectra will obviously give you all the peaks over different wave numbers, but you look specifically in the spectral region between, say, what is this, 1000 to 3000, because that is where you'll see the signature of the graphene. And that is how you dissociate the different elements, like the different materials in the structure.
Okay, thanks.
Okay, so next we have Umeshda, and then Radeep sir, and then Anand sir, then Ash sir.
Hi.
Hi.
Hi, great talk. I had two or three questions. Probably I will ask one, then if but after
Okay,
Sujata
sure.
will ask, then I will come back. So one of the question was that if you go to the plot where you showed that there is a kink at the
Yes.
mm, density. So
Mhm.
my worry is that there are so many experimental noises at every other density
Yeah.
How are you exactly pointing out that there is a prominent kink at the particular density we're talking about?
You mean from like charge, like I guess charge puddles, impurities, or um, like lattice mismatch, stuff like that, disorders?
No, I'm simply asking from an experimental point of view. Let's say you
Yes.
have all these graphs, all these blue, green, and
Mm-hmm.
different graphs, and you are
Yes.
saying that you can see that there is a kink at the
Yeah.
at a particular density of ±1. But
Mm-hmm.
what I'm asking is that at every other density there are these noises in your data. So
Yes.
from that noises, how are you differentiating this kink from?
I mean, these show up as more prominent features and something which is present in all of the systems, irrespective of other noisiness. Like, this is a very prominent feature which shows up in all the nanoparticle system, graphene nanoparticle system. So, I mean, I think this trend is pretty obvious from this graphs though, but I guess what you mean to say is that how are we saying that this is not due to some other effect in the system, some other impurities, some other source of those kink, and just this strain and superlattice? And I guess the answer to that is that if those were coming from other sources, they would have varied erratically in all of these systems, and they shouldn't have shown such a consistent behavior, which is why we're attributing it to the strain coming from the nanospheres. But it is a fact that the data can be quite noisy, which is why right now what we're trying to do is encapsulate the graphene in hexagonal boron nitride. That will give us much cleaner spectrum energy, sorry, much cleaner resistance values, and will give us like better curves we expect. Does that make it clear?
Yeah, it's okay. One quick question, then I will move on.
Okay.
So one thing that you showed for the two different like voltages in the earlier one, for different voltages, you showed that if you have particular voltage, you have different thing. Probably one or two
Oh yeah, okay, I see. Yeah,
in the beginning.
this one. Yeah, I guess this is the one you're talking
Little,
about, right?
little bit. Oh, the two slides. Yeah, this one.
Okay, yeah.
So what I am seeing from this one is that for negative and positive voltage, you
Mm-hmm.
have different resistance nature.
Yes.
So can you explain this, that why there is no symmetry between the, like I
Left
understand
and
as
the
a
right.
voltage. Huh?
You mean the symmetry in the left and the right side of the curve?
No, I'm talking about the symmetry for the voltages. So if you like go to voltage from +50 to -50, so this is
Oh,
simple gate voltage change, right? Or
yes.
not?
Yes,
Yeah.
yeah.
So I thought there should have been a symmetry between the gate voltage flip, but there isn't. So can you?
Yeah. I don't know. This was like done by Corey Dean's group.
I see.
Um, so yes, I guess that depends on what happens physically in the system because of the superlattice, right? And whether that is symmetric about zero superlattice voltage, or um, I think maybe it is possible that even when you have a zero superlattice voltage applied, like for example, even for like there is still some potential in the graphene layer, right, coming from impurities and things, and which is why it might not exactly be symmetric about your zero superlattice voltage. Like there might be effects, but
I
I'm
see.
not sure.
I get your point. Yeah.
Yeah,
That's okay. Thanks. Yeah.
thank you.
Thank you so much, Unmesta. Next, Rajdeep sir, please.
Hi, Preetha. Very nice talk.
Thank you.
Uh, just maybe first one comment to
Yes.
probably Shadnik's question is that you know, the Raman shift going down basically means your phonons are softening, their energies are coming down, stiffness is coming down, and with strain you are basically having softer phonons. That's basically what is happening. But now The question to Preetha is going back to your data on the kink.
Yes.
So here, so I am of course aware of superlattice calculations when you have just potential fluctuations, but
Yes.
you have slightly more, which is you actually have gauge fluctuations which are varying on some particular length scale, which has a periodic character to it.
Yes.
Right?
Yeah.
So my question was, have people actually looked at the theory and you have tried to match to some extent with that? Or
Yes. So I don't have the curve right now, but actually they have, we collaborated with some theory groups, and like very prominently it shows the conductance dips with this gauge field effects taken into. I think some of these references might help, like
okay,
yes, it has been looked into.
Thanks. Yeah.
Thank you, sir. Thank you so much. Next, we have a question from Oyanga.
Yeah, so nice work by the way. So I have two questions.
Yes.
Yeah, so first question is you are using SiO2 nanoparticles for strain,
Yes.
but again in some of the picture I have seen a substrate which is bent in certain way that it feels like it also gives some strain. So why is it that there are two things causing the same strain? Yeah, this one.
You mean this one? Oh, so this these aren't experiments which were done by our group. This was an experiment which was done separately just to study the effect of uniaxial strain, and they used a flexible polymer as their substrate, and this is like just one of the configurations which they give me a minute. So yeah, this thing which I can't pronounce again was their substrate, and they applied like the forces in different directions to strain the graphene. But in our systems, we just have graphene on these nanoparticles. Like, yeah, basically that.
Okay. Okay, so yeah, one other question that
Yes.
in some slide I have seen that the nanosphere size varies from 10 to 100 nanometers. So how you make sure that you are getting a superlattice that is having the same dimension all around?
So in any specific sample, you have nanospheres of just a certain diameter. I don't know. Yeah, so either we are using 10 nanometers, 20 nanometers, or so on.
Okay, so yeah, so these are like different nanospheres that you can get. It is not like varying within a same sample.
No. Yeah, because that wouldn't give you this closed packed structure.
Okay, yeah.
And just, yeah, different nanosphere diameters give you control over the amount of strain you have in the system. But for any specific sample, we use just one type of nanospheres.
Yeah, and one last question. So how you like land this graphene on top of these substrates?
That
so
is a whole,
yeah. So in
Go
our
ahead,
case, we
sorry.
generally use HBN, but in these cases, I don't see like HBN encapsulations.
So in general, there are two techniques for transferring graphene. I think the one you use is the dry transfer, where you have some sort of polymer, and you use that to you have exfoliated graphene, and then you pick that up with polymer and transfer it on your sample. We use the wet transfer technique, because for wet transfer, we don't get very large crystalline regions of graphene, but we require just a few microns of graphene. So that works for us, and it is a little cleaner. So for wet transfer, we usually have graphene which is grown on copper foil using chemical vapor deposition, and we essentially, the graphene floats on water and we scoop it up with our chip. It requires some skill and time, and sometimes it can go wrong, but it's a wet transfer technique. You can look that up. I'm sorry, I don't have an image of it right now.
Thank you. Really great talk. Okay.
Thank
My
you.
questions are
I'm
over.
glad you liked it.
Thank you so much. Just a little announcement. You can either type your questions in the chat box or you can raise your hand. I should have mentioned that earlier. And also, it would be very nice of you if you could just ask one question at a time, and then we will get back to you if there is no more questions left. So that was all. And next, I'll go to our.
Hi,
Sorry.
Preetha, can you hear me?
Yes, I can hear you.
Okay, so you showed towards the end that it's difficult to produce this aligned structure,
Yes.
you know, on which you will put the graphene layer.
Yes.
But for the spherical nanospheres silicon oxide on which the initial results are based on. So
yes.
I mean, it seemed that even there, how you know how regular that structure is and how well the graphene layer has been put on it,
Yes.
that will sort of have some effect on the nature of the strain. And
That
the
is
nature
true.
of the strain also is one of the big factors. So how is it, I mean, do people do it on many different samples and sort of average the results, or how do you ensure that the results are reproducible?
Well, obviously, I guess one of the first things to look at is the Raman's. Like, obviously, there are some things you can look at optically. Like, if your graphene sheet has folded over, there are bilayers, trilayers of graphene, or rips in the graphene. You can observe that just by looking under a microscope from the color contrast. Then we also do atomic force microscope to locate which are the good regions of which looks like the good regions of graphene on silicon nanoparticles, silicon dioxide. Then we look at the Raman spectra. So like if the graphene the peaks, okay, wait, I'll show you. But if these peaks aren't very prominent and there are like D peaks showing up and other things, then that is a signature of disorder present in the system. These are the data which was taken was for specific samples, but yes, obviously you do it over a large number of samples and you just select the best amongst them and you eliminate the others, some of them which are based on noise and other impurities.
Okay, thank you.
Thank you so much, sir. So I don't think there is any more questions other than
Shagnik said, I don't know whether Shagnik asked his question. Because he
I did, but
oh,
SC
okay.
ma'am is
Sorry.
Okay. So am I the last one?
I think so.
Okay. I guess last but not the least, hopefully. So if you go to your slide 27, I think there are many questions about this, like the conductivity.
Yes.
Now, you know, pardon my ignorance. So I see that there is in the x-axis, you have this minus and pluses.
Yes.
This is concentration, I suspect.
Yes.
N?
Yeah.
Is that? Okay. What is that? Why is there plus and minus? Is just normalized, I understand.
Yes.
But what is the idea?
It's that you're varying the charge carrier density by varying the gate voltage. So when you're in the minus side, you're actually having a negative voltage. Yeah.
Okay, got it. Now all these curves are all these things, and they have different stress. Did I understand that correctly? This green, red, black. Now, can you tell me then that why do you have this particular shape of N versus sigma? And why are these like flattening when you have different amounts of stress? Physically, what is happening? Did I make my question? Was I clear enough?
Like physically, why these curves are behaving the way they
like
do?
this. I mean, you see that this is the direct point, the 0, 1, is that right?
Yes.
Okay, and we see that the sigma is lowest there, right?
Yeah.
The conductivity is lowest there. So
yes.
What happens actually?
Okay.
Why does it go that way? Why does it spread when you have different stress?
So what happens is, if you think about why, I'll go back to this graph for a while. So the first thing to note is that the conductivity dips in the Dirac point because there are theoretically no states available at that region. And so the resistance sort of peaks in that region. So you have the V shape in general. What happens because of strain is that there are, so what you'll have is near each of the Dirac point, which was earlier just a cone, you'll have more bands opening up. And as a result of that, there will be secondary Dirac points. So imagine this whole thing on the left condensed and forming a small thing over here. So secondary Dirac points, if when they fill up, then again, there is no state available to the electrons at that moment. So that results in a small kink in the resistance and so on. So it's because of additional levels filling up in between, which lead to those.
Okay, but that number 10 to the 12, does it have any significance? Because it turns out that it's for all those substances.
Yeah, so that
does it have any, this particular number, does it have any significance?
Yes, so if you think about the supercell, like the periodicity of the superlattice, from that too you can estimate and you get the same number. So it does.
I see.
It gives you.
So it is related to how you do your
exactly
substance sample.
That's true. Yeah.
And just quickly, I mean, we spoke about, I think the same issue came in Unmesh's talk, but you have Dirac equation that these are all what? Excitations, virtual particles. Am I right? Or
these are the charge carriers.
Oh, the charge carriers.
Yes.
Okay. Not the virtual.
No, these are not quasi-particles.
Thank you very much, Preetha. Yeah.
I'm glad you liked it.
Thank you so much, ma'am. Thanks, everyone. So does anybody have any more questions?
Okay, so you can
just write it in the chat.
About the interaction session.
Oh, I think Rajdeep sir has another question. Mr. Too.
Yeah, just a small question, Preetha, on that curve where you showed the normalized conductivity. The normalization is that at high carrier density, you basically normalize the slope to be same.
Yes, yeah. Just multiplying it by a factor.
So that's okay.
Yes.
Okay. Thanks.
Great.
And Unmesta?
Yeah, so I had just one small general question for Preetha. Yeah. So you have probably seen many these normal graphene conductivity plots, and you have probably seen this issue that the Dirac cone doesn't really come at the zero voltage or so. So is this because the graphene usually, even though we call it a pristine graphene, it usually comes with the intrinsic doping of?
Yeah, like there are charged puddles in the system, impurities present, and that leads to the shift in the graphene. And also at the interaction between like whatever substrate you have your graphene on, how the charges vary at that. But yeah.
I see. Okay, fine. Thank you. Yeah.
Okay, thank you so much. So if nobody has any questions, we can end this session. But before that, and we will move to the session. Ognivo has some news to share.